Okay, this is my solution for the problem that we did on Tuesday of week 5. And in this problem, we were talking about a cylinder, big cylinder, as a carnival ride, and people lean against the wall, and then the cylinder spins, and the floor drops out. And the people do not fall, and the question is, why? Well, they don't fall because it has to be a normal force on them. Okay, so why don't they fall? Well, they don't fall because of friction. And so, in fact, let's draw the free body diagram here for this person. There's a normal force due to the wall, this way, and there's a friction force this way, and mg is the force of gravity, downward. So what's going on in this problem? Well, this problem has an acceleration inward. And inward means centripetal. It means center seeking, actually. The word centripetal just means an inward acceleration. And this acceleration is v squared over r. So it's just an acceleration, not a force. And so there's in fact only 3 forces in this problem. And the maximum that friction can do as static friction is mu s times the normal force. So I'm going to write down the sum. I'm going to choose axes first, x and y. And I'll write the sum of the forces in the x direction and the sum of the forces in the y direction. And in the x direction, I have the normal force, and that's pretty much it. In the y direction, I have the frictional force goes up, and the gravity force goes down. And in each of these cases now, I know that the sum of the forces has to be equal times of m times a in the x direction and m times a in the y direction. For this problem, we don't want the person to be accelerating in the y direction, so this is 0. And this becomes v squared over r, because we want them to go around in a circle. Now, it doesn't mean that they're getting any closer to the center of rotation. They're not, but they're accelerating away from a path of constant velocity. Okay, so I'll rewrite this system of equations, and I get that the normal force is equal to mv squared over r, and instead of the friction force, I'll write mu s times the normal force minus mg equals 0. So I can combine these equations now, and where I see mu s in this bottom equation, I'll write mu s times, let's see, the normal force is mv squared over r, and that's minus mg equals 0. I can divide both sides of the equation by m, and I find that, in fact, mu s has sort of an interesting relationship. It's now just g times r divided by v squared. And that's the answer. So if you're given, say, an r, a radius r, then you know that the velocity is 2 pi r divided by some period t, where the circle has a radius of r. If you plug that into this value, then mu s is g times r all over 2 pi r over t squared. And so I get, let's see, I have a g and a t squared and a 4 pi squared and 1 factor of r left over. And that's the answer.